Today we're going to look at reaction coordinate diagrams or potential energy diagrams or reaction progress diagrams, however you want to say that. And what we're going to be looking at is the changes in energy as a reaction proceeds. And we can map that out, and we can also talk about the speed of reactions looking at these graphs or these diagrams. So in order to talk about coordinate diagrams, we've got to talk about a few terms first. The first thing we really got to focus on is something called activation energy. And we've talked about it a bit before. But activation energy is the amount of energy required to get a reaction to go. It's the minimum amount of energy needed for a successful collision that's allowing bonds to be broken and bonds to be formed. So that's that minimum amount of energy that those particles need. The greater the activation energy, the slower your rate. Now, why is that? Well, if reactants need more and more energy to collide successfully, then it's not going to be a very fast reaction. So if we're talking about like a reaction at room temperature, well, they would only have an average of 20-25 degrees Celsius. But if the activation energy is like 200 degrees Celsius, very few, if any at all, particles would have enough energy to react. But if we brought that activation energy down, then maybe some particles would have enough energy to react. So here's an example. Hydrogen and oxygen gas can be kept in the same container. Even though hydrogen is extremely explosive, if we heat it to 800 degrees Celsius, or we introduce a spark, they react. And that's because they now have that required activation energy. And we've all heard of the Hindenburg disaster, which is what caused that in the first place, hydrogen gas exploding because of something allowing that activation energy to be provided. So that brings us back to something called the Maxwell-Boltzmann distribution. We spent a lot of time with this last year, and it looks at the average energy of particles. Remember that if we're talking about a system at 20 degrees, that's the average energy. Just like if I said our class average is 70%, well, that means half our students have higher marks and half our students have lower marks. Not everybody has a 70%. Just because it's 20 degrees in the room doesn't mean everything in the room has 20 degrees worth of energy. Some are moving faster, some are moving slower. But temperature is just a measure of that. So if we plot that curve, let's say, for example, we're at room temperature. So this curve represents our particles at room temperature, let's say 25 degrees Celsius. And in order for it to react, it needs to have, let's just make it 100 for easy numbers. Now, at 25 degrees Celsius, no molecules, no particles have reached that threshold, that activation energy. So none of the collisions would be successful. But as I heat up this system, we're going to stretch this curve out. And that means that more and more particles are gaining energy, and more particles are actually starting to surpass. So even though this might only be, let's say, I don't know, 50 degrees Celsius, well, now at this point, even though the average is 50 because that's the middle, that's the average, some particles are higher, and some are even high enough to actually start reacting. So now that means that you have the reaction beginning to proceed. You'll have some successful collisions. And if we provide more and more activation energy, more and more energy to the system, more and more particles, anything past that line is going to have enough energy to react. The closer we get, the faster the reaction goes. Think about lighting a piece of paper on fire. You don't light all the molecules at once, you light one part of the paper, and as that fire produces more heat, it allows more molecules to gain enough energy, and the fire starts to build, and eventually it burns. The whole thing is engulfed in flames. So that's basically what I'm saying. And if we added a catalyst, and that's what is in this lesson here, if we add a catalyst, remember catalysts lower that activation energy. So if I take that activation energy and I slide it backwards on the curve, what you'll see is now more particles will have that energy to react. So that's what causes catalysts to make reactions go faster. They lower the activation energy, so it's easier for particles to react. Remember, the area under the curve represents the number of particles at any energy, and anything past that line tells us the number of particles that have enough energy to react. So as temperature rises, so does the number of particles with enough energy to react. The other term we got to talk about is something called enthalpy. We talked about enthalpy in grade 11. It's the heat content of a reactant. And we can talk about the change in enthalpy of a system, whether it's gaining or losing energy. And basically in order to do that, we look at the change from the products to the reactants. So if the products end up with more energy, then energy has been gained. If the products end up with less energy, then energy has been lost. And we call that a change in enthalpy, and we have terms for those changes in enthalpy, exothermic and endothermic. If we've lost energy from reactants to products, that means that energy has been lost, again, it's gone out of the system, so that's exothermic. And if energy has been gained by the system, that means the energy is going in, so we call that endothermic. Now, in order to look at these energy changes, we draw these things called reaction coordinate diagrams or potential energy diagrams. And what we're doing is we're just diagramming the energy changes during a chemical reaction. Think of a reaction like a roller coaster. To get a reaction to go, you have to apply energy, just like you do with a roller coaster. The first part of a roller coaster ride is long, slow, and uphill. And the whole purpose of that is to provide the carts with enough energy to complete the ride. If they didn't get enough energy, it would be a pretty crappy roller coaster ride. Once the carts reach the top, then they have enough energy to complete that ride. And that's at that point where you crest the hill in the roller coaster, you are now activated. You have enough energy, the ride is going to happen, and you will finish that reaction or that ride. So reactants with that amount of energy are called the activated complex. In a chemical reaction, the energy is added to overcome that activation energy and form that complex. So this is what a potential energy diagram would look like. And we would start with your reactants at some energy. We're not really even putting numbers to this, we're just sketching this out. But you have A and B at a specific amount of energy, and then energy is going to be added until you get to that specific amount of energy, that activation energy. So here's kind of the beginning of your roller coaster. You've got to add energy, add, and then once you get to this point, now the collisions are successful. So that's what we call our activation energy, or our EA. And once that happens, the reaction takes off. And once it takes off, the energy will change. Now it could end way lower, it could end way higher, depends on the reaction, but at the end of the day, it's always going to be this kind of a shape. And where you start to where you end, that difference in energy is our delta H, our change in enthalpy. So in this reaction here, our reactants started up here. These are our reactants with this much energy, and our products ended here. So our energy went down. So this is an exothermic reaction because we've lost a specific amount of energy. And that's what they would look like. So all exothermic reactions will have a coordinate diagram that looks a lot like this. The hill, that big hill at the start, is our activation energy hill. The bigger the hill, the longer this reaction takes to get going. So it's a slower reaction. And then if it's an exothermic graph, you're going to see that their delta H is negative. So we started higher than we ended. If we're talking about an endothermic graph, it'll be the same idea. You still have the big hill at the start. That's your activation energy. But our delta H is positive this time. So our products picked up energy over the course of the reaction. So they're at a higher energy state than the reactants. So if we have this reaction, here's a typical coordinate diagram for it. If we look at this, our activated complex is what's at the top there. The way I think of it is it's just all the reactants mashed together. They're in the middle of a successful collision, just mush everything together on the reactant side. The activation energy for this reaction, they've shown us on the graph, is 88.9 kilojoules per mole of that chemical. And the change in enthalpy is negative 77.2. Notice we always have a sign on our enthalpy change because we want to say whether it's gaining or losing. So in this case, it lost. That tells me that this reaction is endothermic. Now, soon we're going to find out that reactions are reversible. So if I wanted to reverse this process, I would be starting on this side and I would be heading that way. That's the reverse reaction. So to get this reaction to reverse, in theory, I would just have to apply enough energy to get back up to that activated complex, which would be the sum of my two energies. It would be 166 kilojoules per mole. More on reverse reactions as we go, but we should be able to understand that to go reverse, we would start at the products and we end at the reactants. We're going from right to left rather than left to right. So when we're sketching coordinate diagrams, that's just what we're going to do. We're just going to be drawing a sketch, and that's all this is. So what I've done here is I've sketched what this coordinate diagram should look like. So I start my graph wherever I feel like starting. I just start somewhere in the middle, and I'm going to add energy. So I'm going to draw a hill. And that hill, I labeled it as my activation energy, and it has 45 kilojoules of energy per mole. And then my delta H, since it's negative, my reaction has to end lower. So I make my reaction come down lower than my initial value, and I labeled that as my delta H. So there is my coordinate diagram for this reaction. Sometimes reactions are reversible, so here's a try this one, but I'll just go through it with you. If we're talking about this reaction, the forward activation energy is 60 kilojoules per mole. So you'll see that I've drawn my hill and I labeled that as my activation energy. But since the delta H is positive 45, I've got to end higher than I started. We'll try to make our scale kind of relative. I'm not so worried about the scale. I'm more worried about the shape, where you start, where you end, and knowing where the activation energy and the delta H should be measured from. So my delta H, I started at this height and I ended at this height, so my energy went up by that difference. Now, if I asked for, and the question does, for the reverse reaction's activation energy, we're just starting at the end, so we're starting here and we're going back to here. So to get from here back, I'm going to have to apply energy from this point to get it up to this point. Now, since this whole hill right here is 60 kilojoules per mole, and I know that this part of the hill is 45 kilojoules per mole, I know that that distance would be 15 kilojoules per mole. Obviously not to scale, but that's how we would get backwards. So you can do some of the potential energy diagram graphs and check your answers with the keys provided and see how you're doing with that.